Here we have the second example for node analysis. We want to find the current I2 in this circuit. Find I2. Okay, by node analysis. Okay, here is the circuit. We have a voltage source, resistor, capacitor, another capacitor. We have dependent voltage source. We have an inductor, and we have a resistor. Okay. The values for these elements and power supply is the 20 cosine of 1000 t minus 45. The resistor is 5. The capacitor is 5 microfarad. The other capacitor is 1 microfarad. The dependent source is 3I1. The inductor has a value of 100 millihenry, and the last resistor has a value of 10 ohms. I1 is the current moving through 10 ohm resistor, and we want to find I2, which is the current moving through the 5 ohm resistor and 5 microfarad capacitor. The first thing we need to do is converting this circuit to the phasor mode because the elements we have here all are in like time domain, and we need to convert them to phasor. The first element we want to do the conversion is the voltage source. We know that the voltage source with the voltage of 20 cosine of 1000 t minus 45 in the phasors is 20, which is magnitude, with an angle of negative 45, and of course omega, which is the angular frequency, is 1000. Okay, now we need to find the phasor of the impedance of the capacitor. So the impedance of this capacitor is negative j over omega c. Omega is 1000, c is 5 microfarad. If we substitute these values, we will have negative j 200. The other capacitor, which is 1 microfarad, is equal to negative j over omega c. Again, this one will be equal to negative j 1000. The inductor has a value of j omega l, which is equal to j 100. And for the resistors, the impedance is the same for it's the same as the resistance. So now that we got to this point, we need to identify the nodes. The first node is here, which is V1. The second node here is V2, and third node is here, which is V3. Okay, we should know that all this part considered as a single node. And one more thing we should notice here is that between V2 and V3 we have a voltage source, and we know that in node voltage analysis, whenever we have a voltage source between two nodes, a super node will be created. So we have a super node here. Okay, now it's time to write the equations. Now that we reached to this point, we start writing the equations. We start by writing node 1 voltage. Okay, node 1 V1. because it's connected directly to a voltage source, we simply say V1 is equal to 20 with the angle of negative 45. The next node, because V2 and V3 create a supernode, we need to write a supernode. So node 2 and 3, which is a supernode, will have these equations. So the voltage, the current leaving V2 toward V1 is V2 minus V1 over 5 minus J200. 5 is corresponding to the resistor and negative J200 is corresponding to capacitor, plus V2 over negative J1000 plus V3 over J100 plus V3 over 10 is equal to 0. Okay, let me show you each part. So this one is for this current. This equation is for this current. This equation is for this current, and this equation is for this current. Okay, so total of these four currents are equal to 0. The next thing is the constraint. The constraint we know that V2 minus V3 is equal to V2 minus V3 is equal to 3I1, 3I1. Okay, what is I1? I1 itself is equal to V3 over 10. So instead of I1, we know that I1 is equal to V3 over 10. So we replace V3 over 10 with I1. So we will have V2 minus V3 is equal to 3 V3 over 10, and as a result V2 minus 1.3 V3 is equal to 0. So first equation, second equation, third equation. Okay, then as usual we can just substitute V1 in these equations and to have two equations with two variables. If we substitute V1 in this equation, because we don't have V1 anywhere else, so we will have two equations with two variables, or we can just leave it as is. In the last example, I just substitute the value and converted the like three equations to two equations, but here I'm going to keep it as is and write a 3 by 3 matrix in just to show you how to solve these problems without these substitutions. So if we put these values in the matrix, we will have 1, 0, 0, negative 1 over 5 minus J200. The next term is 1 over 5 minus J200 minus 1 over J100. Third term is 1 over J100 plus 1 over 10. Okay. The third row is 0, 1, negative 1.3 times V1, V2, V3 is equal to 20 with the angle of negative 45, 0, 0. And as a result, V1, V2, V3 are equal to 20 with the angle of negative 41, 1.29 with the angle of 38.2, and 1 with the angle of 38.2. Okay, you see that we got all three voltages, but in fact we did something redundant, like here. We calculated V1, which is equal to 20 with angle of negative 45, but we already knew it. We knew that V1 is equal to 20 with the angle of negative 45. So we didn't have to go with matrix 3 by 3, but I just showed you that even if we solve in this way, the answer is correct. Now we need to find I2. Let's go back to the circuit and see what is I2. I2 is V1 minus V2 over 5 like minus J200. Okay, so I2 is equal to V1 minus V2 over 5 minus J200, which is equal to 20 with the angle of negative 45 minus 1.29 with the angle of 38.2 over 5 minus J 200. Okay, don't forget that we need to convert this one and this one to rectangular, then subtract, then convert back to polar, convert this one to polar, then divide them. So we have several steps to do this division. So I2 will be equal to 0.1 with the angle of 39.9. Okay, so we got I2, but if we look to the I2, we see that it's in the phasor mode. But the problem, like once we find I2 in time domain, so we need to convert it back to time domain. The only other information that we need is like the frequency, which is 1000. So we can simply say I2 of t is equal to the amplitude cosine of the angular frequency, which was 1000 t, plus the phase. So this one is the final answer. Okay, let's move on to the next example, which is like another circuit with more elements. Example: use node voltage analysis to find voltage gain K, which is VO over Vs, and input impedance Z sub int. Okay, so here is the circuit. you see that the values are given in the phasor form, but the voltage source is in time domain. Okay, we have all values, and we need to see where is the VO. VO is here. And one more thing, the Z in is the impedance seen from this point, and I in, of course, is here, and that's it. So this one is the circuit. The first thing we should notice that is, in order to find the Z in, we need to like find the voltage of this point and divide it by the current, so it gives the Z in. Okay, so let me just solve this circuit. The first thing, converting the voltage source to the phasor, which is 10 with the angle of 0, and omega is 10 to the power of 5. Then identifying the nodes. So here we have node VA, node VA. Here we have node VB. Here we have node VC. Instead of VC, because all of these parts are same, we know that VC is equal to VO. So let's call it VO instead of VC. So this one is VO. And here is the reference point. And that's it. So let's go ahead and solve this circuit. We write there is no super node, and so we only need to write KCLs. Okay, KCLs, node A. Oh, one more thing before like solving this example. I had other option as well. I could like say here we have other node. Let's call it V D or VC, and we know that VC is equal to this voltage source, okay, and say VA minus VC over the resistance. Okay, we also have this option, but in order to like minimize the solution, we don't like consider here as a node. We do not consider as a node, since the voltage is known. The voltage is 10 volt with the angle of 0. So since the voltage is known, we don't need to consider it as a node. The same thing is true or applicable for other examples. So here we could like say we have only two nodes in our previous example. We could say we have one node here, one node here. There is no node here, and the voltage here is equal to 20 with angle of negative 45. Okay, it's the same as considering V1 as a node and then substituting the value. By not considering this, let me just erase these extra lines. Oh, okay. So, but not considering this like point as a node, since the voltage is known, we get rid of a substitution step. So we don't need to do substitution. We directly, instead of considering V1 as a node, we just apply the voltage. So we don't need to like do the substitution or go with like larger matrices. Let's just do in this example. In this example, we start by solving this circuit. So we say VA minus the voltage, the current moving from VA to the voltage source. VA minus, what's the voltage at this point? We like not considering this point as a node, but we know the voltage. So we say VA minus 10 with the angle of 0. Okay, so we know the value over 50 plus VA minus VO for this branch, VA minus VO over J100 plus VA minus VB for this part over negative J50 is equal to 0. Note B. For node B, we say VB minus VA over negative J50 plus VB over J10 plus VB minus VO over negative J20 is equal to 0. Node O, the last node, we can say VO minus VA over VO minus VA over J100 plus VO minus VB over negative J20 plus VO over 50 is equal to 0. So here we have 3 equations with 3 variables, VA, VB, VO. Let's factor out VA, VB, and VO from these equations. So we will have 1 over 50 plus 1 over J100 plus 1 over negative J50 times VA plus 1 over J50 times VB plus negative 1 over J100 times VO is equal to 10 with the angle of 0 over 50. So first equation. Second equation, 1 over J50 times VA plus 1 over negative J50 minus 1 over J20 plus 1 over J10 VB plus 1 over J20 VO is equal to 0. This one is the second equation. Third equation, we will have 1 over negative J100 times VA plus 1 over J20 times VB plus 1 over J100 minus 1 over J20 plus 1 over 50 times VO is equal to 0. Now that we reached to this point, we need to substitute these values in the matrix. So we will have negative 1 over 50 plus 1 over J100 minus 1 over J50. We have 1 over J50. We have negative 1 over J100. The second row of the matrix is 1 over J50. It is 1 over J50 minus 1 over J20 plus 1 over J10. The third column, second row is 1 over J20. Third row is negative 1 over J100, 1 over J20, and finally 1 over J100 minus 1 over J20 plus 1 over 50. So this one is the first matrix multiplied by VA, VB, VO is equal to 10 with the angle of 0 over 50, 0, 0. Okay, and if we do this matrix multiplication, we will have VA, VB, VO is equal to 8.3 with the angle of negative 21, 1.1 with the angle of 115, 2.9 with the angle of 168. So we got VO. So we have VO and we know what is the VS. So voltage gain, which is VO over VS, is equal to 2.9 with the angle of 168 over 10 with the angle of 0, which is equal to 0.29 with the angle of 168. So this one is the gain. What is Z in, input impedance? Let's go back to the circuit. Here, the circuit, the input impedance is the voltage at these 2 points over the current entering to this circuit. Okay, the first thing, the current entering to from the left side of the dashed line to the right side of the dashed line. Of course, we can simply find it. We can say this the volt Vs minus Va over 50. So Vs minus Va over 50 is I in. Vs minus Va over 50 is I in. So we need to just divide VA by I in. Okay, so let's do that. Z input impedance is VA over I in. What is I in? First, let's find I in. As I explained, I in is Vs minus Va over 50, which is equal to 10 with the angle of 0 minus 8.3 with the angle of negative 21 over 50, which is equal to 0.07 with the angle of 53 amp. So we got I in. So we can say input impedance is equal to VA over I in, which is equal to VA has a value of 8.3 with an angle of -21, and I in has a value of 0.07 with the angle of 53, which is equal to 111.2 with the angle of -74 ohms. So this one is Z in, or we can convert it to because it's impedance, we want to know what kind of elements are in this impedance to our resistance, capacitance, or like in inductance. We convert it to the rectangular form. So Z in will be equal to 30.9 minus J 107. So it tells us that the resistance part of this impedance is 30.9 ohm, and impedance part, reactance part is negative 107. So it's like capacitive inductance because the reactance is 0, so it considered as a capacitive conductance. So if we want to do an equivalent circuit for this circuit, we can say, okay, we have our voltage source Vs, we have the 50 ohm resistor which is before dashed line, and after dashed line we will have another resistor with a value of 30.9 and an capacitor with a value of negative J107. So this one is equivalent circuit. This one is an equivalent circuit for this circuit. So the equivalent circuit for this circuit is like this circuit. You see that we don't have any inductor in this circuit because inductors and capacitors cancel each other, and capacitor in total was like stronger than inductors in this circuit, and then gives the capacitance reactance at the in the output. So if you are asked to draw or find the equivalent circuit, you can say this is the equivalent circuit of the example. Okay, so that was the node voltage analysis for AC circuits.